Have you ever wondered why physics professors can pretty much teach any course in physics at the undergraduate level, while in other areas that's not true? You may have, say, like social psychologists, or you might have a chemist that's analytical chemist, or a physical chemist, or organic chemist, inorganic chemist, or a botanist, or someone who studies fish, or someone who studies micro biology, or DNA, and they don't easily they can't really teach all the courses in their major. And this class will show you why, basically. And it's going to be hinging on the Laplacian. Laplacian's our topic for today. And the mathematics looks very similar in like all the upper level courses. And this is good news for you because it makes you powerful. You can go into engineering. The Laplacians used in engineering, used in all areas of physics. And to have this foundation is very, very important. However, when I was department chair, I had trouble justifying getting a new position in physics because I couldn't say we needed to have an optical physicist, or, I mean, there are nuclear physicists and elementary particle physicists, there are specialties, but because of this Laplacian and the mathematics being so similar, you can teach anything. So it was hard for me to compete with, say, another department that says I need to have a physical chemist because no one can teach the physical chemistry course. I can't ask the organic professor to teach it or the other, so I need to get that. And then the dean, the logic would be, well, look, you all can make your physics classes a little larger in size, and you can cover, and you can wait. In other words, you can wait a little bit longer. I said, but no, we got a lot of students, man. Should we get more faculty positions? He says, well, yes, but we got to take care of those that need the specialties. All right, so in some sense, it was a little frustrating, but I would never trade it in because I think that the power of being able to teach in so many different areas is worth it. And it's worth it for you to have this kind of power in your education that by majoring in physics, you could go into all kinds of fields, and astrophysics, electrical engineering, meteorology. They're all using similar mathematics, just with different symbols. All right, let's go on and see what it's all about. Chapter Q, the Laplacian. Q0, the wave differential equation. I'll say DE. Now, we derived this equation earlier in our course. Second derivative in space and second derivative in time. And I mentioned earlier, I remembered the class in optics where the professor derived this. And then I have fond memories of my mentor at the University of Maryland when he was teaching this, that he said that the V goes with the T because distance, like x, is velocity times time. That's one dimension, 1D. Now in 2 dimensions, we would get a y and an x involved in the wave. And in 3 dimensions, 3D, we would have x, y, and z. And if you're dealing with the speed of light, with light you would just change V becomes C, but these are general wave equations, differential equations. So now we go to Q1, operator notation. This operator here, which appears in so many physics courses, the del operator, is defined as I hat partial with respect to x, j hat partial with respect to y, k hat partial with respect to z. There we go. All single derivatives. I often write the I hat, j hat, k hat to the left, because in some coordinate systems, like when you have theta hats and, you know, they differ, they're not constant. So here there's no mistake that we're not going to take any derivative of any of the i's, j's, and k's, but we're going to be operating on something that's to the right, like a function. Then if we take the definition of the dot product, now remember when you do this dot product, if you have like two vectors, an A vector, say with an A x, I hat, a y, j hat, and a z, k hat, and a B vector with some bx, I hat, by, j hat, and bz, k hat, then when you take a dot product, you can look at this as having, you know, 3 terms here and 3 terms there and a possible 9 terms total. But when I hat dot I hat's going to be 1 and I hat dot j hat going to be 0. So this comes out to be very, very easy. AX, BX, and I guess they should be consistent here. I'm using lowercase. Let me just use the lowercase here to be consistent. Plus AY, BY, plus AZ, BZ. So this is A dot B. And a lot of books will use uppercase and just write it like this. So either way is fine. All right. Another way of looking at it. So here, when you come in there, you're going to get then the partial. If I write this out, dx plus j hat ddy plus k hat ddz, and do the dot with I hat. Just copy it down again since it's going to be with itself. I dot I will be 1. I hat dot j hat be 0, because another way of looking at your dot product is this is saying A times B, the magnitudes, times the cosine of the angle between the two vectors. It's always good to remember that form also, so that if you're perpendicular, you're going to get cosine of 90 is going to get you 0. So here, I dot I will survive, j dot j, and k dot k, and that's going to get you then second derivatives. All 3 are going to be second derivatives. So that would be here the second derivative with respect to x, plus the second derivative with respect to y, and the second derivative with respect to z. And this is written as del squared like this. This is your Laplacian. So this is the definition of the Laplacian, which is the main subject of today's class. Let's take a look at Laplace. Laplace is amazing. Worked in physics, mathematics, engineering, and he's known especially for the Laplacian, which we just looked at, and the Laplace transform, which is used a lot in engineering. So smart and ahead of others of his times that he became known as the Newton of France. Just like Isaac Newton was ahead of his contemporaries, such a genius. We consider Isaac Newton and Albert Einstein as the 2 best physicists of all time. So he's being compared to Newton. So now if we look at the wave equation, we can write this equation here in a compact form. See, the Laplacian operating on the wave equals 1 over, and I'm going to use C here since we're going to be in vacuum for this discussion on this topic here. So we get this in vacuum. That is the wave equation for the speed of light. So light waves. Nice. Now, what I find very interesting about this kind of an equation, and I think it's worth writing out again, the star equation in our course, you might think. Is that if you were to subtract, let's subtract these and have on one side, keep this here and then take everything here and put it on the right-hand side so it's then subtracted. And this is fascinating because this equation agrees with relativity. You know how a lot of equations you write down are not quite right? Like if you write down F equals ma, I mean, they're right in their proper frame, but when you look at the realm, but if the velocity is a lot less than c, then you can use Newtonian mechanics, and like it's correct. An engineer study that. Nothing wrong with that. In fact, that's good stuff. But when you get to higher speeds, then a lot of those classical equations, break down. They're not true. They have to be modified. This does not have to be modified. This agrees with relativity. And one of the key things that you study in modern physics is that whenever you see the c squared, say, and like a delta t squared, and then minus delta x squared, you have the space and time with the minus sign like this. That's a good sign that relativity is being obeyed. This shows up a lot. You've probably seen stuff like this in the modern physics class. And this combination does not change when you go from one inertial frame to the other. Remember, special relativity, you have a frame of reference called the K frame, and then that's at rest, and then you have a K prime frame, which is moving at speed v, and then the equations in this frame and that frame have the same form, you see, and they have the same form. They'll have the same form. This one will have a t prime, an x prime, a y prime, and a z prime, but you'll have the same speed of light. Speed of light's the same, and then you have the same form. You'll have this, they call that an invariance or an invariant. And the Maxwell equations that lead to the wave equation, relativistically we say invariant. That means they agree with relativity. So the secret is in the Maxwell equations and the wave equation, and if Einstein didn't discover that, someone else would have. But Einstein's the one that figured out what was going on, the special theory of relativity, and that's 1905. And then the general theory, 1915, which is a theory of gravitation. Now this combination is very, very cool. And I want to bring into discussion here D'Alembert. Now, D'Alembert, a mathematician, a physicist, a music theorist, he discovered the wave equation in one dimension. He was interested in strings and music, and he derived this equation working with the physics of the string. And then here he showed the two solutions, traveling to the right and left. We already did this little quick review here, and to bring in D'Alembert because one of the operators I'm going to tell you about in a second is the D'Alembertian and relates to the waves. So the D'Alembertian operator, this is a cool operator. This operator takes the Laplacian and has the 1 over c squared, the partial derivative with respect to time, second derivative, and then minus the Laplacian. So this operator here, when that operator operates on the wave solution, you get 0. So you can think of this as just subtracting the del squared psi here on both sides, and then on the right-hand side, you'll get the second derivative with respect to time minus the Laplacian. And this brings us to what's named after D'Alembert. And D'Alembert, by the way, with Denise Diderot, co-authored, I say co-editor, but the main, the editors behind the first encyclopedia. And this was during the time of the 1700s, the time where in European history they refer to as the Age of Reason or the Enlightenment. And the encyclopedia of knowledge, they started putting together like all the knowledge together into like a series of volumes, the encyclopedia. So this here is defined as the D'Alembertian, the box. Now that means we can write the wave equation as the box or the D'Alembertian. Now that is very cool. There you go. That's the wave equation for light. Crazy, all right, isn't that cool? So, D'Alembertian. We want to study today how the Laplacian looks in spherical coordinates, mainly, since that's very, very important in lots of your courses. So let's look at this. And the first coordinate system we're going to look at in somewhat detail. Let's go ahead and call this section coordinate systems. And the one in detail that we all know about is the Cartesian system. Cartesian system you learn about in high school, where you put x here and y. That's the Cartesian system. And then we add z, later. And there's Descartes, named after René Descartes, Cartesian. Very, very famous philosopher. In fact, some refer to him as the father of modern philosophy. Famous for his I think, therefore I am. His starting point in building a philosophy. Very, very impressive. And a mathematician, the X's and Y's, and analytic geometry, like where you're looking at geometry with the coordinates X and Y, and a physicist. So here we have the Cartesian coordinate system, X and Y, developed analytic geometry. That's pre-calculus. You often encounter that first in high school. And gave a derivation of the law of refraction. Right, now that goes back many centuries to Arabic and Persian scientists, and in modern times later he rederived it. We talked about that earlier, and he calculated 42 degrees for the primary rainbow without calculus. That's amazing. All right, all impressive feats. So let's review the coordinate systems. So we want to look at A, Cartesian, and we want to look at B, cylindrical, and then C, we want to look at spherical. You've probably seen this before. Hopefully I will add a little different twist to it and show you how we can derive the Laplacian in all three coordinate systems. Well, you already have it in Cartesian, but show you how to get it in the others. So you've probably first seen this in math class, but let's go ahead and review it. So you have the x-axis, I have the y-axis, and we have a z-axis. And then we can come out here with r. This is like your distance. You pick some point here, or at some point. And we mentioned this already, where you can think of this as having a door, where this is an angle at theta, and then if you take r times the cosine, you get the height of the door. So that would be the same on either side. This is r cosine of theta. And then r sine of theta gets you the top of the door, which I would like to call rho, because down in here, when you have this nice rho, you have polar coordinates, where if you have phi here, then you can look at here, this is rho times the cosine of phi to get you this adjacent side. Here's a little tricky on paper to do this, but see, that's really a right angle. So this is a right angle because you're like perpendicular to the y, you're perpendicular to the x. So if that's a right angle, then that's your hypotenuse is like opposite. So rho times the cosine gets you this side, and then rho times the sine of phi gets you this side. So we can do this, rho cosine phi. So it's good to master this, and I know you've seen it before, this is a little bit of review, but we're gonna go beyond this. Now let's go ahead and put the vectors down. Little unit vectors, you got k hat is with the z, you got I hat and it goes with the x, and you got j hat, and you always should check that I cross j does equal k. It's a right-handed coordinate system. I cross, go into j, gonna point up. Now here we go. This is r hat, a little unit vector pointing along the r coordinate. And then if you swing this theta down, it would be pointing in this direction. So that's a theta hat. And then the phi, that would be moving in the other dimension. A little bit hard to sketch all these. This would be here, the phi. But just to show you that each coordinate system has 3 unit vectors. Now for your cylindrical, if you look down here for cylindrical, pointing straight up is your k hat, and that's one of the cylindrical coordinates, is to use z. But then to use the rho and the phi. So the rho, that would point outward away from the origin here in the xy plane. And then here, if you swing to like increase the phi, you're basically doing something like this, the phi hat. So they all have their unit vectors and they have their variables. So everything's on the page here, like all 3. The Cartesian would be x, y, z. The cylindrical would be rho, phi, z. And the spherical would be r, theta, and phi. So I really like this diagram. It's got everything there. And one thing we have to be careful of is that these vectors in general, say, are not constant. In other words, if you bring this r over here somewhere, then r hat points in a different direction. Along here, r hat points along the y. Say along the y. If the r were up here, then r hat here would point at z. So these are not constant. Like your I hat, j hat, k hat are constant. Like they're fixed. They're not going to move. But these are going to move around as you move around the point, and that's why I'm careful to put those to the left of derivatives. So if you're taking derivatives, I put the I hat to the left, because in general, they will not be constant. Now we come to understand why physics teachers, professors can teach pretty much every class at the undergraduate level. Now, you don't need to write this down. I just want to give you a little survey. Here. Poisson's equation that you find in mechanics, where you have gravitational potential, Laplacian. I just want to focus on this Laplacian shows up. Electromagnetic theory, the Laplacian, again, this is called Poisson's equation, and you have one in electromagnetic theory, you have one in mechanics. In thermodynamics, the heat equation, there's Laplacian. That the Laplacian working on a temperature is proportional to how the temperature is going to be changing in time. Quantum mechanics, the Laplacian. This is the Schrödinger equation. The time-independent Schrödinger equation. The time-dependent one has over here an IH bar, partial psi with respect to t. But this one's encountered often, the time-independent one, Laplacian. The wave equation in optics, Laplacian. So now you can see why a physics professor can teach all these courses. Can teach a course in mechanics, electromagnetic theory, thermodynamics, quantum mechanics, and optics. You just change the symbols. It's the same math, basically, similar math. Unlike chemistry, where if you're an organic chemist, inorganic chemistry is a big change. And then if you go to analytical chemistry, or if you go to biochemistry or physical chemistry, these are big changes. And there's specialization, just like in biology, you have botany, or to study, another studies birds or something like that, or microbiology. But see here, a physics professor can pretty much teach any of these courses. Now we do have our specialties in different fields, like solid state physics, astrophysics, elementary particle physics, etc. But the point is that you can teach all these. So this is very powerful for you to learn this class, because this is the basics for engineering applications where Laplacians start to show up all over the place. Q4, curvilinear coordinates. Now let's look at coordinates again in general. You have x, you have y, and you have z. You come out here, you come out there. What I'm trying to do here is show you a little volume element, which a little bit tricky to do with the spherical coordinates, right? And if you can't draw that, no problem. I have a nice picture in the book for you, drawn very nicely. So here, this part here is a dr, a little increment in the radial direction. And then if you look at this one here, this would be a d theta. So this part here would be an r d theta for that part. And then when you go in this other way, this is dealing with your d phi. But remember that if we had, say, going down here in the xy plane, then this little delta phi here, that's going to be hit with the rho. This is your rho, so this is rho d phi, but remember rho is r times the sine of theta, the door. Remember the door, the top and the bottom of the door. So that means your third one here, that's back here, like this one here, is r sine of theta d phi. So let's look at the volume element. It's very, very easy to do it in Cartesian because you just have a cute little cube, and that's going to be a dx, a dy and a dz. So in Cartesian, the volume element is dx, dy, and dz. Now cylindrical is the next more complicated, because in cylindrical, you basically have this. If I go out here, I have a delta delta rho going out, and this is rho delta phi, and the third one's delta z. So this is going to be rho d phi dz. You might want to think of that rho as going with the d phi. So rho times d phi is that little piece there. Then the d rho comes out. I'm forming myself here a little patch. And then if I come up in a z, a delta z, that's the same. So it's basically this patch in polar coordinates, which is d rho times rho d phi. And then you hit it with the dz, and then just pull the rho out the front there. And then the volume element for the spherical coordinates, we just do length times width. Go ahead and multiply these out. And you will get an r squared sine theta dr d theta d phi. And don't worry about this little difference here. Let's look at this. You might say, well, this is dr, and this is r d theta. Isn't technically this one r plus dr times d theta? Because it's got that dr, extra dr added to it, and you're saying it's the same. Well, you see, if you work this out, you get r d theta plus dr d theta. Now, when you take these things going to zero, this is quadratic in a small value. This is linear, so this thing's going to go faster. So in calculus class, they'll just go ahead and do this, and it's like no big deal. So don't let that bother you. Okay, so then we come to a cool little table I like to write. And I like to write here, say in general, I'm going to call the coordinates in general u, v, w. And some books will go with like q1, q2, and q3. And other books might go with x1, x2, and x3. I'm going to just use u, v, and w for now. So I would have, say, x, y, z for Cartesian. I would have rho, phi, z for cylindrical. And then for spherical, I would have r, theta, and phi, the 3 dimensions. And then I'm going to write here h1, h2, and h3. And these are called scale factors. And it tells me if I need to put something in front of the dx or dy, dz. Well, I don't here, so these are all ones. But when it comes down to this one, remember that this rho went with the d phi. So that means I need to put a rho. The phi is the second one listed. Notice d rho and dz are by themselves, so we put 1 there. So if you look at this little q, we do the spherical one next. This has dr by itself. There's nothing in front of it. This has a d theta with an r in front of it. And then this one here has a d phi with the r sine theta in front of it. So I want to put down what's in front of these things here. So for the dr, nothing's in front of that, so that's a 1. For the d theta, I got an r in front of it, so I put an r. And then for the d phi one here, this is the d phi one up here, all right? Then that would be r sine theta. So I put the r sine of theta. So I have that cool little table. And then the next thing we're going to do is try to understand here the d volume element is simply saying h1 times, here you can think of it as the du, that's like the first coordinate, and then h2 times dv and h3 times dw. And with this table, I can write down all the volume elements. So in general, you might imagine some kind of weird looking volume element here. Let's say we come down like this. Maybe do that. That kind of weird looking thing there. So this would be here, like you can think of this one, let's say this one's the first one. So h1 times du, and then this other dimension here, h2 times dv, and then going up would be h3 times dw. And I drew one for you in the book and put some color in there to help see, the top and the bottom. So then if you know the h's, you can write down what the dv is, because see, the dv is going to be, length times width times height. You're going to multiply all those things together. And that's called curvilinear coordinates. So you have a little, curve here, curvilinear coordinates. And now we're ready to do the big jump to the gradient. So let's go to Q5 and look at the gradient. Now here is the way the gradient works. You can think of the cube again for Cartesian, little cube there, and to say this is a delta x. And at this point here at the right, say there's some function that has a value of x plus delta x, but the same height as the one over here, and you don't have changed the y, so this is going to be f x, y, z. So this point's x, y, z, and then you're going to move along the x direction, a delta x, and get this function. And we want to see what the derivative is. But before I do that, let me just review. When you have your x and your f of x, which is y, and you want to take a derivative, you simply look at the function in two places. You pick a point, say that's f of x, then you pick another point over here, and up there, this height here would be the f of x plus delta x, like that. And then what you do is you take, if you blow this up, where you have it blown up here, if you're going to shrink it down and take the limit to go to 0, then it's going to match the line like a triangle. And then this would be here. This height here is your rise, and this is your run. Your run is simply delta x, and your rise is you take the function at the top, which is the one with the x plus the delta x, because see, your x is going to be over here on the left, and this point here is your x plus delta x. So when you subtract, you're going to get f of x plus delta x minus f of x, and this is your derivative. You then take the limit of the rise over the run, so you have the higher value, and you subtract the lower value to get the rise, and you recognize this as a definition of your derivative. I mean, this is the derivative of f with respect to x. So over here, I'm doing the same thing. I'm going to make a subtraction, and I'm going to have a partial derivative here because I have more than one variable. So by subtracting these two, I'm going to have the partial of f with respect to x. That's going to be the limit as delta x goes to 0 of f of x plus delta x, right, y z minus f of x y z. Same idea over delta x. And for the gradient, what I'm going to do, if I do grad, this is the symbol, the gradient, this is going to be the same thing. This is going to be the same thing, but I'm going to then stick the I hat on there, which tells me the direction in which we're, increasing or decreasing. So then you would have the same thing and just stick an I hat on the end. All right. Which would be simply then the partial of f with respect to x I hat. And then if I do that in 3 dimensions, I'll have one for the x, y, and z. So you can see that when you put the del operator on a function, now this function here just has values like temperature. That's called a scalar. That's a scalar function. Okay, so we're going to do this. You put the f in there, the f there, and the f there, and that's going to then add directions to those increases, and that's a vector. So this is a vector. The gradient of a scalar is a vector. It has magnitude and direction. Now to do this in general with some weird looking some weird looking coordinate system, then let's look at these 2 points and say this is the u, say like the u is pointing this way, u hat. Then this here has a scale factor. It has h1 delta u, all right? So now when you have the function here, u v w, over here it's u plus delta u v w. But now when you subtract this one from the big one, say this is the second one, subtract and then divide, you got to include that h factor. So now what you get is the limit of delta u go to 0, you have f of u plus delta u, and this would be v w minus f of, this is a u. We have u, the variables are u, v, and w. So x becomes u. So this is u, v, w. And now we're going to divide by the h1 times delta u, because that is your definition of, forming a derivative. You take, the change in the function divided by the delta thing here, which is h1 delta u. So that means the gradient in general is going to be the first unit vector 1 over h1, the partial of f with respect to, and now I'll go ahead and use q1. In other words, we're going to say u v w. Now we have the general formula. We're going to go to the q notation. And then plus the second one with its scale factor, df, dq2, and the third, and this is the gradient in curvilinear coordinates. Like, that's amazing. So see, if you go back up to here, you would write this as 1 over h1, the partial of f with respect to u. See? And I just need to have one of those, because then I'm going to have 3, when I put them in there. And remember, when you're doing the gradient, you need to attach the unit vector in that direction. So you need to slap on the unit vector on there. And then when you do it 3 times, you do it for all 3 cases, you have the general formula. Okay, so this is the gradient in general. But if I want the operator, I would just have the del by itself, and I would then have E1 hat 1 over h1 partial with respect to the first coordinate, and then I would have E2 hat and then 1 over h2 partial with respect to the second coordinate, and then the third unit vector 1 over h3, the partial with the third coordinate. Okay, now we look at our table. For Cartesian, all the h's are 1, and then q1, q2, q3, x, y, z. All right, so that means, and this is I hat, this is j hat, and this is k hat, the master formula. Okay, now we go to cylindrical. Well, the cylindrical, the first variable is the row, so we have a row hat, and then we're going to have a scale factor is 1, so we have the partial with respect to row, and then the next hat is your phi hat, scale factor is row, so it's 1 over row, and then d phi, and the third one is your z, so this will be a k hat, and it's just partial with respect to z. This is amazing. Like, look at this. And then you can have that operate on some function of say rho, phi, and z in cylindrical coordinates. You go ahead and take the gradient of that thing. And then for spherical, the first one is r, so we'll have an r hat, and the h is a 1, so that's ddr. Since the h is a 1, you just have the derivative with the first coordinate, which is the r. And then we go here to the second one here is theta, so it's theta hat. And then you got the h is an r, so you have to go 1 over h, and that's the partial with respect to theta. And the last one is the phi, and that's going to have for its h r sine theta, and then you take the partial with respect to phi. That's it. You got the gradient like in all three. That's cool. A little meteorology here. The temperature is a scalar. Like at each point there's one value. It's like in mechanics where they have the speed, but then when they add the direction, that becomes a vector. So if you just have the magnitude, in this case, the magnitude is the temperature. But if you take doing gradients, like how's this temperature increasing from 36 to 40, you could draw a little arrow and you take the gradient of the temperature function, you get then the gradient, the change of the temperature. And here's a cool one with wind. So little arrows. Since the wind, you got the length of the arrow is the speed and then the direction. So that is a vector field. Another vector field, here's a plus charge showing little arrows going out. The strength, it's stronger closer to the charge and it gets weaker, so the length gets shorter, just like the wind speed. If it's shorter than smaller, it'll have a shorter arrow. Q6, the divergence. Now we're leading up to the Laplacian. That's the star for today. And to understand the divergence, we're going to draw another coordinate system here with x, y, and z. And we're going to work in Cartesian coordinates for the beginning to get a feel for what's going on. So we'll make a nice little rectangular box. Make it it's going to be a cube because we're looking at dx, dy, dz. So this is here going to be your delta y, and then this is delta x, and then this is your delta z. And we're going to look at a vector field. I have a vector field at the bottom and at the top. So this is the vector field at the top, and this is the vector field at the bottom. And we're going to make the E field very, very simple. Now, it can be a function of x, y, and z, but it's always going to point up. So it'd be k hat. All right? And if you look at this, perhaps if I can draw a little better perspective here. Like there's the bottom, so we can like keep it lined up. So in other words, at the top here, you have the function, and you could put a little z here to just emphasize that this is the z component. And that would be at the top, you would have x, y, and a z plus delta z, because this is delta z here, this height. And down here, the vector, the z component, is just x, y, and z. So we want to look at the integral, which we've seen before. It's a surface integral, where you look at the E piercing the surface. Now here, the E skims the surface here. And remember the way the dA works. If you have a patch of area, then the dA points perpendicular. So here, we're along the perpendicular, to that area patch. That's going to count. This is going to count, but it's going to go negative because the little patch here, the normal, would be down, and the normal would be up here. So you have to look at that what the vector is doing at that surface. Here, it's lined up. So you're going to get here for the contribution. You're going to get here at the top, x, y, z plus delta z times delta x and delta y. That's basically taking the top piece. The roof has the dA is your dx and your dy, dx and dy. And then you have the dot product, and it's lined up, so cosine of 0 is 1. And then you're going to have down here, it's going in, and your normal vector goes down, so it's a minus sign. You might think of this as what goes out is positive, the divergence, leaving the little volume, and what goes in is negative. So what goes in is negative, and what goes out is positive. So you have then this equation. Now comes the big secret trick. If you divide by delta z and multiply by delta z, a marvelous thing happens. First of all, you can factor out the delta x, delta y. So you have then z component at these coordinates, and then you're going to subtract it at the xyz place, and this is over delta z. But then you have this cool delta x, delta y, delta z, which is a dv, like a delta, say volume, a delta volume. This is a partial derivative of vz with respect to z. And see, this becomes a dv. And when you look at this, you got yourself a volume. You're integrating over that volume. And then this is the famous divergence theorem. E dot dA is equal to a volume integral. And see, you'd have one here if you did the other dimensions and included the E field in more generality. You would have a dEx dx plus a dy dy plus a partial, and that is the divergence. See, that's what you would get. This here is what's sitting in there. So that's a very important formula or theorem, the divergence theorem, in vector calculus, the divergence theorem. Okay, we're almost there. We have to get to the divergence theorem in curvilinear coordinates, then we can do the Laplacian, because the Laplacian is the goal. And why is that the goal? Well, when I was an undergraduate and I saw this, I went, yikes. Like what is this, all right? And they throw that at you in quantum mechanics. They'll throw that at you in electromagnetic theory. They'll throw that at you in optics, is what we're doing. And I feel that we should try to understand where that's coming from and take some time. Remember the philosophy of derive everything, that I don't understand something unless I derive it. I'm deriving this for you. That's the whole idea of today, all right? To derive the Laplacian in spherical coordinates, which you use in so many courses. So if we want to set up the same kind of situation in some weird volume element, so let's look at this here where we're looking at some kind of like weird volume element. Now, you're going to get a better picture in the book, where I carefully, drew things in curvilinear coordinates. So here I will attempt to copy from the book, which I used a graphics program playing around with to get something to look nice. So let's say here, this is close enough. So out the top is an E field at the top, and that's going to be, if I use my terminology, say this is going to be H1 delta U. Notice that the scale factors are in there, H2 delta V, and this is H3 delta W. So my 3 coordinates. And then I'm going to have here something going in. So this is top, and this here is bottom, B-O-T-T-O-M. So the bottom one is going to be a function of U, V, W at the bottom. And then here at the top, it's going to be that U, V, W plus delta W. All right. So I play the same game. I say, well, what is going out is going to be E, and I'll put the little reminder that this is pointing in the W direction, which is my Z earlier, W direction. And then I multiply by the area. Well, what's that? That's H1 delta U for this part, and this is H2 delta V. Now before we had delta X and delta Y because the H's are 1. And then this is going to be evaluated at UV W plus delta W at the top. Let's do the top. Then we're going to subtract the 1 at the bottom. So the 1 at the bottom, I could write the same thing down here. The same thing down, delta U, H2 delta V, and just remind myself that this is at U, V, and W. So down in here, we haven't done the delta Z to delta W yet. So when we do that, we can see we play the same game. We're going to divide by the third, the delta Z before, but now we're going to divide, in this case, we're going to do the trick, divide by delta W. I can always divide and multiply by the same thing, all right? So if I divide by delta W, multiply by delta W, is no problem. It's the same thing. And the reason why I want to do that is because this then becomes a partial. If I take out stuff, so let's go ahead and take out stuff now. We want to take out, we're going to take out here, if we take out delta U, delta V, and delta W, and let's leave everything else inside for now. So this is EW times H1 times H2 evaluated at, and I'm just going to put here W plus delta W, that the U and the V are the same. And then I'm going to subtract the same thing where it's at W. Now notice here I'm getting, and divide by delta W, I'm getting the partial derivative of the EW with the H1 and H2, and these can't be pulled out because remember these are functions like R and thetas and stuff, they're functional coordinates. So I have this cool partial derivative with then du, dv, and dw. Now to make sense with what we did before is we wanted to have a dv, but see this is not dv because remember the dv, you have those scale factors. dv is h1, h2, h3, du, dv, dw. So if I divide by h1, h2, and h3, then I'll bring the dv into the calculation. And then in here, what I'm going to have, when I generalize this was the third case, the one over here, E, W, H1, H2, with respect to W. So the first one would be the U one. So if we have here the partial with respect to U of the E U one, then see these two were the other two dimensions. So the other two dimensions here would be 2 and 3. You see? And then here would be the other one, which we can just simply say would be the V1, and the other dimensions would be 1 and 3. Because when you're taking that vector that's going perpendicular, you want the other two dimensions for your area. So now we have the divergence. The divergence here in general, and I'll go ahead and write down del dot E. This is the divergence. This is going to be, remember, the divergence was everything that I had inside that integrand, and I had the dv, here it is, the dv on the far right. Everything that was inside here is the divergence. So if I collect everything that's inside here, and this extra stuff, because I just want the dv by itself, I have 1 over h1, h2, h3, and then I have the partial. I got the 3 partials. This is going to be able to put the q1 here. We'll do the q1. This is e1, and this is going to be h2 and h3, and then this is going to be q2 with e2, h1 and h3. Remember, these are the ones that are different. And then if I go Q3, E3, the different ones would be H1 and H2. all right? So that's it. This is the divergence in curvilinear coordinates. And if we would like to check for Cartesian, remember Cartesian, all the h's are 1. So all the h's are 1, they're all gone. And then you're going to have then the derivative of E1 here. It's going to be E1 is your x, so it's the EX with respect to x, plus E2 is y with respect to y, and this is z with respect to z, all right? What about the case for cylindrical? Well, cylindrical, H1, that was the row 1, that's a 1. H2 was a row, and H3 was a 1. You consult your table there, but you remember that the row went with the d phi, So I would then have, if you want to put it in, you could, 1 like this. Just put in 1 for H1, row for H2, and 1. And then here, you would have the derivative of E row, and whether the two other ones, row is this first variable, is your row, and this variable, the second one is your phi, and the third one's your z. So you would have here the row. This would be row times 1. This, if you're dealing with this one's the other 2. Remember, 2 and 3, 2 and 3. And that's the derivative with respect to row. And then you would have here the derivative of phi. And what's H1 and H3? Well, they're 1s. So times 1 times 1. All right. And that would be here with respect to phi. And then finally, the EZ, what's 1 and 2? Well, 1 times row. So that would be, there would be a row here and DZ. That's it. That's the divergence in the cylindrical coordinates. Okay, so for spherical coordinates, we've got the table up here. We're looking at these three where the H1 is a 1, H2 is R, and H3 is R sine of theta. And then the Q1 is R, the Q2 is theta, and the Q3 is phi, looking at the master table there. So all we have to do is now be patient, and that 1 is going to be the electric field vector along R, and then 2 and 3, I'm just going to go to my 2 and 3, that's going to be here, R squared, if I go ahead and put the parentheses there, R squared sine of theta, and that's a derivative with respect to R. So out in front here, I'm going to have 1 over R squared sine of theta, which comes from the product of the h's. Then if I come in here, I want the derivative, partial derivative. I'm looking at the second coordinate, which is the theta one, and H1 is a 1, and H3 is R sine theta. So I would have R sine theta here, and that's with respect to theta. And then the last one is E phi, and H1 is 1, H2 is R. So that's just going to simply have an R up in there, and that's going to be with respect to phi. Okay, now if you look at all this, the theta is independent of the R. So that means for the first term, what's going to happen here is that this theta, this sine of theta is going to cancel that sine theta. Now you can't pull the R out because you have a partial derivative there. So I have the partial derivative of ER, and there's going to be an R squared up in there, all right, with respect to R. And this R squared survives. Sine squared canceled. And then over here, this R will cancel this, one of these, so I'll have here an R sine of theta, but I can't pull the sine of theta out because this is the derivative with respect to theta. So here, we're going to have the E theta sine of theta up in there. And then finally, this r will kill one of the r's in the r squared. So we'll have 1 over r, and the sine of theta will survive, and we'll have the partial of e phi with respect to phi. Amazing. So now we're ready to go to the climax. The climax is 07, the Laplacian. Now to do the Laplacian, what we're going to do is what we looked at earlier, del dot del. That's what we did before to get the Laplacian. But I like to have something on the right here to grab onto. So we're going to take the gradient and then do the divergence. But we have the definition here for the gradient. We already did this. 1 over h1, the partial of f with respect to q1, and that's going to be the e hat 1. Now, when this derivative is clearly that just applies to there, I'm okay putting the e hat on the right, because it's clear that derivative is only on the f. So if we do that, we'll get the partial here, q2 and e2 hat plus 1 over h3 f dq3 e3 hat. And then the divergence, which we'll use a here, we already worked this out. This was the product of the h's down in the denominator. Then it was the partial of the first component times the other h's. So the first component, 2 and 3 for the other ones, and that's your q1. Then when you do the second component, then you want h1 and h3, the other ones, and that's q2. And then the last one, you want h1 and h2, the ones that are not h3. And there we go. So all we have to do is take this thing and basically call this like A. In other words, if I want to call that A, then I take the divergence of A. So I'm going to basically plug in for the A1, what is the A1? Like this is A1. This is A2, and this is A3. So what I need to do is put that A1 in here, the A2, that needs to go there, and then the third one has to go in there. So really it's straightforward. Got to write down a lot of stuff, but that's okay. All right. So if we do that, then we'll have the Laplacian acting on f. So we'll have the h's here, and then we'll have the partial with respect to the first coordinate, and then what's going to go inside here, well, the a1 is 1 over h1. We're just going to copy from up there, the f dq1, and then we're going to have the copy, h2 and h3, and then the parentheses. So this derivative of all this, just the a1 is this part here, which we just copied from up above. And we do the same thing 2 more times. So that's going to be the partial with respect to q, and this is going to be 1 over h2. You can almost like figure it out from the other one. The partial of f with respect to q2, and then I have here 1 and 3. So I got the first part from up here. I got the h1 and the h3 from there. And then the last one, if I do the partial with respect to q3, the a3, I just copy from up here. It's 1 over h3, but see, they're looking the same. And then partial with respect to q3. And then I have h1 and h2, and I got it. Like this is it. Perhaps a little bracket on this one to include everything. That's Laplacian. That's it. So if you want the Laplacian operator by itself, you're going to have H1, H2, and H3. And then we're going to have the partial with respect to Q1. And then in here, what I'm going to do here, I need to be very careful. I'm going to move these H's over to the left in here because it's very important that if I put here the partial with respect to Q1 as an operator, that this was only going to operate on the F. Say that's a self-contained unit, so I better put these H's over to the left since I'm writing this in operator form. Now I have to be careful. And you could, kind of see what the other ones are going to be. If this is a Q2, then I'm going to have here 1 and 3. 1 and 3 over H2, the partial with respect to Q2. And then here, the partial with respect to Q3, I'm going to have the H's 1, 2, H3. See, it's kind of neat how the 2 goes with the 2, the 1 goes to the 1. You can start to see all these relationships here. It looks kind of nice. And the partial with respect to Q3. Now, I'm going to do here for you the spherical case, which is the one we're really shooting for, Laplacian spherical coordinates. Solve the hydrogen atom. When you do the Schrodinger equation, you got this. So to do that, H1 is a 1, and H2 is R, and H3 is R sine of theta. Remember the big 3. Then over here, this is the partial with respect to the first coordinate, that's R. And then 2 is an R. 3 is an R sine of theta. And H1 is a 1. And that's the derivative with respect to R again. Then for the theta derivative here, H1 is a 1. H3 is R sine of theta. H2 is going to be R. And that's going to be the derivative here with the theta. And the last one is the derivative with phi. H1 is 1. H2 is R. And H3 is R sine theta. And that's the derivative with respect to phi. Okay, so now we look at this, almost finished. Here, this sign will cancel that sign, and this R squared will survive, 1 over R squared, and this will be the partial with respect to R, and I'm going to have an R squared up in here, and another partial with respect to R. That's it. That's what we had earlier. That's the Laplacian so far. And then here, I can't mess with that sign, but this R's cancel. And then I have out front, I have R squared sine of theta. And then I have d theta, sine of theta, d theta. And then for the last one here, well, I have here, look at this sine theta and that sine theta, that's going to get me 1 over R squared sine theta squared. I probably shouldn't have crossed those out like that. That wasn't a good thing to do, but I think you can see where this is heading. And then these R's cancel. And then that sine can go right out because sine, the theta is independent of the phi. They're independent, so that comes out. Just like the R could have come out, but it got canceled anyway. And this is then the second derivative with respect to phi. That's it. Like that's it. Like we got it. That's it. That's amazing. I'm going to end here on a note of my calculus teacher from undergraduate days, Mr. Samuel Enzer. Now, Enzer, he had us derive the Laplacian the long way in Calc 3. He gave us a month to do it. And see, I was able to do it here with the curvilinear coordinates and introduce you to curvilinear coordinates all within this one class. But he says, I want you to start with the Laplacian and Cartesian coordinates, and then I want you to do transformation of variables, because you know what x, y, and z are in terms of r, theta, and phi. And I want you to do these partial derivatives and you go nuts, man. You go crazy. It's like this is the long way, and it did pages and pages. But I really appreciate that he had us do that, because I became really expert in taking partial derivatives and using the chain rule. And it's worth doing. Now, I don't want you to do that because during the semester you're too busy, but you know, maybe like during your break, maybe during the break, to do it. It's very worthwhile. It's like an exercise routine where you're exercising and jogging, you know, to perfect things, and then you go play some other sport, but you're exercising. Mr. Enzer. We do have a bonus, by the way. Let me show you the bonus. Since we had this theorem, the divergence theorem, and we know from the Maxwell equations that this is equal to the charge over epsilon naught, you can integrate over the volume the charge density. And if you do that, you get the Maxwell equation in differential form, like a bonus, like we got one of them. And this one here, because that's equal to 0, you get this. So we got half of the Maxwell equations in differential form as a bonus, and I'm going to leave the other two for the electromagnetic theory course. So that's where they should do that. But this is kind of neat that we were able to get that far.